Hello, everybody. Good morning, good afternoon, and good evening, depending where you are. We are here from the University of East Anglia, and my name is Alberto Troccoli. I'll be chairing this webinar related to the European Climatic Energy Mixes activity under the C3S. I'll explain in a minute what that is. The title of the webinar is Explore European Climate Bias Adjustment and Multivariate Approaches. So the European Climatic Energy Mixes ECEM is a component of the Copernicus Climate Change Service program run by ECMWF on behalf of the European Union. And ECEM specifically has developed, in close collaboration with the energy sector, a demonstrator to assess how well different energy supply mixes in Europe will meet demand over different time horizons, focusing on the role climate has on the mixes. You can find much more information on the website here, including a link to the demonstrator, which I don't encourage you to do now because we've got very good talks coming up. So just hold on for an hour or so before going to that link. And there you'll also find the registrations of previous webinars, as well as this one when we're finished and the audio is produced. Just a brief word about the overall activity with the ECEM. What we did was developed calibrated climate variables, and these are the variables that are most relevant for the energy sector. And this is pretty much the focus of today, although this is only what we're discussing today is only a small component of all the work that has been done under this area of climate variables. The climate variables were then converted into energy variables, and this component also was a very large proportion of the activity, which is partly displayed in some of the webinars, also past webinars. Again, you can refer to them on through our website. The results obtained were then assessed through some case studies and some other ways that are also have been presented on webinars and on some of the publications that we're producing. And ultimately, all the data went onto this demonstrator, which is shown here. Just this is an old image of the demonstrator, but you find a lot of information about climate variables, energy variables, on historical period projections, the assessment of seasonal hindcasts, and so on, with a lot of documentation here on the bottom left-hand side of the demonstrator. The agenda for today is as follows. So we'll have two presentations. One is on multivariate bias adjustment based on empirical distribution transformations. And this is given by Dr. Sylvie Paré of EDF in France. And a second one is bias adjustment procedures for wind speeds used in ECEM, with assessment also of the latest ERA5 data. And this is by Professor Phil Jones at the University of East Anglia, who's here with me. So we'll hear from him also later. This is also part, let me say, that this, although we did a lot of work to obviously prepare the data for the energy sector, we also wanted to make sure that all the climate data were as best as they could, of course. This is the basis of the work we've done. And as part of that, also we've done the this multivariate adjustment work, which is quite leading edge work. And so it's great that Sylvie can present this work in a minute. I just wanted to tell you how the webinar then will proceed. After the presentations, we'll have about 10 minutes for question and answers. And also the webinar is recorded, and as I said, it will be available on the website. And you can ask questions at any time. There is a tab on your GoToWebinar control panel. So at any time during the talks, you just ask a question, and we take note of that. And at the end, we address all the questions we received, or most of them. And that's it. Enjoy the webinar. And I just now give the floor, so to speak, to Sylvie. So Sylvie, over to you, please.
Thanks, Alberto. So good afternoon, everyone. I'll be talking to you about multivariate bias adjustment, as Alberto just said, and the tests we've made in the framework of ESEM, the project Alberto just presented previously. And I will give my talk along these points, first reminding what is bias adjustment based on distributions, and the hypothesis, and then explaining how this is generalized to multivariate distributions. And I will show some results using first synthetic variables and then real climate data before ending with the next steps of this study. So as everyone knows, climate models simulate large-scale climate variables. And so if we have to make impact studies, we need generally observed meteorological variables. All the tools developed are based on observed meteorological variables at for a small area or even for a precise location. So there is always a need for bias adjustment and downscaling. And the distribution-based techniques, just like quantum mapping or CDFT, are commonly used, and they adjust the distribution of the model variable by that of the observed one, either at the same spatial scale, if we just have to bias adjust, or at a finer spatial scale, if we both bias adjust and downscale the outputs of the climate models. So typically, for such studies, we have at our disposal 3 distributions, which we can draw from the time series we have. We have observations for the historical periods and a model simulation for the same period. Generally, we have this. And we have a simulation given by the same climate model for a future time period. And what we would like to have is what would look like the observations for the future period. And this can be done from the material we have, but we have to put some assumptions in order to do the transformations. And we have 2 choices for these assumptions. First, we can choose to assume that the transformation from the climate model to the observations will be the same in the future as it is in the historical period. And this is called here hypothesis H31, or horizontal, because the arrows here are horizontals. So this is how it has been nicknamed in Howard studies. And this is the common assumption, the general assumption made when using empirical quantile mapping, for example. And we can too have another way of doing and taking another assumption, which is that what is stationary is the transformation between the historical period and the future period, as this has been computed by the climate model. And this transfer from the historical to the future is assumed to be the same for the observations. So this has been called in our work hypothesis H32, or vertical, because here we have the red vertical arrows indicating the stationary assumption, which is assumed here. So this is true, whatever the distribution we have. This is true for univariate distribution, and this second assumption is typically that which is done for CDFT, for example. But we can have exactly the same assumptions when using multivariate distribution instead of in univariate ones. But to generalize such approaches to multivariate distribution, we had to to base the work on a mathematical background, and this is based on a theorem which states that whatever the distribution, when you take the distribution of one variable conditionally to all others, and you do this for each variable at a time, then you end up with a uniform distribution. And this allows to compute transfer functions from one distribution to the other where you go through this uniform distribution. So you compute each distribution for each variable conditionally on the other ones. Condition that you begin by one variable, then the second one condition it to the first, and so on and so forth. And then you can take the inverse transformation from this uniform distribution to get the transform distribution from the first one. So this has been coded and tested first in using synthetic data in order to control the parameters and the differences we can have between historical model and historical and future. And this has been based on the simulation of bivariate Gaussian distributions. The parameters of the distribution have been taken mimicking the behavior of daily mean temperature in July in two different locations. Here, this has been taken from the European Climate Assessment and Dataset Project database for Hamburg and Hawley for the periods from 1979 to 2014. And then we had two means, M1 and M2 are the averages for the two locations, and we have the variance and covariances. And using these values for the means, variance, and covariance, we can simulate bivariate Gaussian distributions, that is, distributions simulating consistently both variable with one bivariate distribution. And then this is used to simulate a distribution representing historical observations. And we had to make some assumptions to simulate in the same way something which could represent the model simulations of the same variables and the model and observation in the future period where there has been some climate change. So the hypotheses which have been made here have been to consider model errors in order to simulate the model simulation variables for the historical period. And we have chosen to take two types of errors, some moderate errors, some errors in the mean and in the variances. The mean errors are taken additionally, while the variance and covariance errors are taken multiplicatively. So we have used moderate and large errors between the observations and the model simulation. And in order to mimic climate change, we decided to take into account a moderate increase in temperature and in temperature variance, or large increases in temperature and temperature variances. And we tried to make different assumptions for both variables and for the different variances in order to have something the most mixed possible mixed, the closest possible to what we could have in reality. Then with this set of parameters, we can simulate a bivariate distribution for the observations over the historical period, one for the climate model in the historical period, just using the model errors. Then we can simulate one bivariate distribution for the model in the future using both model errors and climate change. And we can simulate a bivariate distribution for the future period for the observations, just using the climate change. Of course, in ordinary situations, we don't have the observations in the future, but here we can simulate them, and this can be used to compare the bias-adjusted variables which we obtained from the climate model to the truth we have here, but which we don't have used for the training of the methods. So from the three distributions, we can use different bias adjustments, both using both previously presented hypotheses for each variable separately or on a multivariate basis. So this leads to 6 types of corrections, the 2 univariates according to the different assumptions, and for each and the two bivariate corrections, but we here with the bivariate corrections we have 2 possibilities, because we have to begin with one variable and then correct the other one conditionally to the first. So we can begin with the first variable and then adjust the second conditionally to the first, or begin with the second variable and then adjust the first one conditionally to the second. So we have 6 types of corrections or adjustments. And then in order to judge for the accuracy of the performance of the bias adjustment, we chose to compute a ratio between the distances of the bivariate distributions, the obtained bivariate distributions. We first compute the distance between the bias-adjusted bivariate distribution and the future observations. And we divide this by the distance between the future climate model bivariate distribution and the observations. So the obtained ratio indicates how closer we are from the future observations than was the climate model simulation. So a ratio lower than 1 means that the bias adjustment has been efficient. If it's higher than 1, then it's not efficient. Here we can see the results. These box plots are based on 30 simulation. In fact, I explain you how I simulated the bivariate distributions, and this could be done here. It has been done 30 times in order to have a sample of these bias adjustments and have a distribution of the results. So these box and whiskers plots indicate the results for these 30 trials, and for each of the bias adjustment methods in 2 cases, one with large model errors and small climate change, and on the left on the screen, and on the right we have the same with small model errors and large climate change. First, here we have all the distribution. We can test the stationarity of the transfers, and in the case of large model errors and small climate change, we found that what is rather stationary is the transformation between model and observations, so it's H31. Whereas when we have small model errors and large climate change, what is much stationary is the transfer between the historical period and the future period. So this is assumption H332. And the results here are showing that, as we had expected, the transformation or the adjustment based on the hypothesis best verified or give the best results. So here we have for the large model error and small climate change, what is called the horizontal bias adjustment giving best results as the vertical bias adjustment, and the contrary is true when we have small model errors and large climate change. Here we have 2 types of distances between this. This is why we have 2 graphs for each case. we used two types of distances between the distributions. One is just the L1 distance and the other one is L infinite. So each one is based on the distance between the L1 distance, and the L infinity is based on the max difference between between both distributions. Then we tried different types of correlation between both variables in the bivariate setting, and we ended up with the conclusion that the strength of the correlation does not seem to have any impact on the robustness or on the results of the bias adjustment. So this is true whatever the strength of the correlation between both variables. Then the same type of bias adjustment, bivariate bias adjustment, has been tested using real climate data. Here we have used temperature and wind because, yeah, I forgot to mention it, but one assumption of this methodology is that the variable has a positive distribution on the definition domain, and for example, if we had taken rainfall with the mass on 0, we would have had troubles, for example, when inverting the distributions. So we first tested the method with temperature and wind speed for Hamburg, again taken from the EKND dataset for a long period between 1950 and 2015. And for the climate model, I'll just use one climate model, the IPSL climate model used in the CMIP 5 exercise, and just downloaded the closest point to Hamburg. And this, considering this long time period, allowed us to divide the period between two sub-periods, one for calibration and one for validation. And these sub-periods were large enough, 33 years, so that the estimation of the distribution can be quite robust, but not too long, so that we can, in a first approximation, neglect climate change over the period, so that we can consider that the distribution is stationary. But if we want this stationarity hypothesis imposes to do it on a monthly basis, because we have the seasonal cycle and we have to deal with the seasonal cycle. So the bias adjustment has been conducted on a monthly basis. That is 1 month at a time. And using hypothesis H31, because this was the most verified in this case, because we have two very, very close subperiods. So this corresponds to a case with small climate change. And we again compared independent univariate bias adjustment to this bivariate bias adjustment using either temperature first or wind first. So this table shows the results with first the comparison of the correlation given by the observations and the climate model. And for each type of correction, bivariate or univariate correction, each gives the distance ratio, that is the performance of the bias adjustment, and the correlation. And what we can see here is that globally, in bold, we have the best distance ratio obtained by the methods. We can see that generally the bivariate correction performs better or at least performs better for more a month than univariate adjustment, but the differences are not huge. We don't have a real gain in the adjustment using bivariate correction. But what we can see too is that when the climate model has a strong error in the correlation. For example, here is highlighted in May or in July, where the correlation between temperature and wind given by the IPSL model is quite far from that which is observed. Then bivariate bias adjustment has the potential to improve this bias from the model, whereas univariate, of course, doesn't change the correlation given by the model. So this is the main advantage of using bivariate correction, knowing that this is more time, computer time consuming than univariate correction, and this is a little bit more complicated. So we have more distribution estimations, and so more estimation errors potentially. So here we can see it has an illustration, but this is not very clear. Here we have in black the bivariate distribution obtained from the model in blue and from the observations in black. For May on the left and for July on the right. And we have the two plots on the right are the distribution before correction, while on the left we have the same distribution but after either univariate correction or bivariate correction. And we can see that there is a small improvement when using bivariate correction, and this is mostly due to the improvement of the covariability or the correlation between both variables. So coming to the discussion conclusion, so we have developed a multivariate distribution correction based on mathematical theorem, and which is quite general, whatever the number of variables. But we have to bear in mind that the more variables we have to consider, the more variable, the most information we need to have to fit the model. For example, if we have here, we did it for 2 variables. So if we had 3 variables, we would have needed to have much more data to train the technique. So here we've shown the role of the stationary hypothesis, which probably is much more important than the fact that we had just both variables at the same time or each variable independently. And now we have to extend such consideration to rainfall distributions, to improve the coding, and then to further test these 2 hypotheses, even in the univariate context. So that's it. Thank you very much. And here is the paper, which is now published in Envirometrics.
Okay, thank you very much, Sylvie. That was a very nice explanation of the approach you explored and pioneered here with your work during ISEM. And again, I encourage people to put their questions on the control panel here. And while we switch to the next speaker, I just wanted to re-emphasize again, like Sylvie said, that this is a particularly important work to look at this bivariate and ideally also linking more than 2 variables, because as we know, when we correct one variable by itself, we don't know what's going to happen to the balance of the other, and this is particularly important when we're looking at the balancing energy, for example, various supplies and demand and so on. So that was a big driver in what we've been doing, although as you can see, it's not a particularly easy task. But obviously Sylvie has done an excellent job at that, and I just want to now switch to the next speaker. So Professor Phil Jones is going to talk to us about the some of the issues we found in the bias adjustment with the ERA interim data, particularly for wind speed. And I'm just trying to get go to webinar to agree with my screen. I think I've managed now. So over to you, Professor Phil Jones. Thank you.
Okay, thank you, Alberto, and good afternoon, everyone. So I'm going to be talking today about some of the wind speed adjustments we've made within ECEM, and then some comparisons with station data, and particularly some station data in the northwest of Iberia, so in northwestern Spain, in Galicia, and in Portugal. And I'll do that through some distributional comparisons of station data with ERA interim and also scatter plots. And then in the second part, sort of the last third of the talk, I'll talk about some comparisons of ERA interim with the new ERA 5 data set, which I'll mention as well. And this is for the period 2010 to 2016. So in ECEM, we've assessed ERA interim by comparison to observational data across Europe. And I'll be talking here mostly about the wind speed data. There's a little bit left about the other variables occasionally. And the emphasis is going to be in the station data is going to be in northwest of Iberia, particularly in Galicia and Portugal, where we notice some anomalous adjustments in our bias adjusting technique there. And just a reminder that ERA interim, despite being a very good reanalysis, is not perfect. And we can assess how good it is one way or another in different places and times in Europe by comparison with observational data. And improving on that is bias adjustment. And the bias adjustments I'll be talking about, in contrast to the ones Sylvie spoke, are about univariate bias adjustment. So we're adjusting wind speed without any regard for the other variables. And similarly, we're doing temperature independently of the others and precipitation, etc. So here's the variables we looked at within ECEM, and it was air temperature, precipitation, solar radiation, and relative humidity. But I'll be talking about the wind speed at 10 meters. Now within ERA 5, there will be another variable where they will estimate wind speed 100 meters above the surface, so it should be more relevant for many wind turbine applications. ERA 5 is available for the 7-year period, and comparisons with ERA interim over that period. Now, we've had to degrade ERA 5 slightly, and we're upgrading ERA interim to a common resolution in all these comparisons, which is a half by a half degree latitude longitude. And we're also working on the ERA interim 6-hour time steps. But ERA 5 will be available at an hourly time step, but observational data to compare that with is still only available at the 6-hour time steps. And ERA 5 is at a finer scale than this half by half degree latitude longitude. And in a previous webinar and in this paper here in Earth System Science Data in 2017, we've discussed a number of approaches that have been available in the literature. Most of these are independently produced, i.e. are not involving multivariate bias adjustments that Sylvie talked about. And most of these were introduced for bias adjusting GCMs and RCMs, i.e. climate projections, where the biases compared to observations are much larger than they are for reanalysis. So you can read more about our bias adjustment technique in this paper, and particularly for wind speeds, you can look at this paper by Tai et al., which uses the Weibull distribution to look at wind speeds in tropical areas, in particularly tropical cyclone wind speed distributions. So we use different distributions for each variable, and for wind speeds, this was the Weibull distribution. And for the observations that we're comparing with, there isn't a gridded data set like EOBS or ECA&D that Sylvie talked about. There isn't satellite data which you can get for irradiance, So we reduced to station data, and we're taking data from the Hadley Center ISD dataset, which is sub-daily measurements of various variables at stations. And we're taking the wind speed from them, and we also took the dew point depression data from that data set as well. And there's all the details of that in the paper in 2017. Now, in the paper, we discussed whether bias adjustment was worth it. And in the project, we followed that through to look at the data in the energy variables. So were the energy variables different with using the bias adjusted data or the original ERA interim data? So there's some discussion there. And in the future, once ERA 5 is fully complete back to 1979, we're going to need to look at this again. Because although ERA 5 is probably better, it ought to be better because it's an improved model, it's at finer spatial resolution, it's finer temporal resolution, you still would like to compare it with observational data. And you've heard Sylvie talk about the multivariate adjustments here in the previous talk. Now, within the project, we've used a number of real-world data sets. I've talked about them, and they're here. And HAD ISD is mainly for wind speed. We're also going to bring into some of the plots that are coming a data set called WFDEI, which is the watch forcing data applied to ERA interim. So this is a bias adjustment to ERA interim directly from station data, and it's applied on the global space scale, not just over Europe, where we've been working in ESEM. But it's important to know what real-world data sets they have used in order to do this bias adjustment. And they've used similar ones to us. And the key point here is that they state that WFDEI is unadjusted ERA interim data for wind speed. But in the plots you're going to see, this isn't always the case. And this is probably a function of how the different groups have transferred the spatial scales of the data from the ERA interim grid to a latitude-longitude grid, and at what time steps they've done that. So the first thing to look at is some station distributions. So these are distributions of where HAD ISD has time series long enough to do something with. So Europe is pretty well covered with data. There are obviously period areas of better coverage than others, but these are the station data. And here we're looking at the observational fitted parameters and comparing them to the ones we get after adjusting ERA interim and then using that grid box where the station is. So on the left, you have the Weibull scale parameter. This is the 2-parameter Weibull distribution. And on the right, you have the shape parameter. So you can see most stations have very similar shape and scale parameters after adjustment. But there are still some. You can see a few in the left-hand diagram around coasts or in mountainous regions, and maybe a few more in the shape parameters in the alpine region, where you have larger differences, which means that either the observed fit of the Weibull distribution wasn't very good, or the adjustments haven't improved, haven't forced the ERA interim back towards the station data. So, but there's about 800 stations here, so there's an awful lot of things to look at and find out possible reasons as to why some of the fits weren't as good as we hoped they would be. But the emphasis here is going to be on Iberia, because we noticed some odd things happening here in the demonstrator work. So we got this is the network of stations across Iberia. We've got a number of stations here. And I'm going to show you some distributional plots and scatter plots, mainly for stations in the northwest here, particularly numbers 6 and 7, which are Pontevedra and Vigo. Stations 31 and 32 in Portugal, 32 is Porto, and 31 is another station in northern Portugal, and 1 or 2 other stations which you'll know roughly where they are from the names. Later I'll show you a few other stations in the direct comparisons with ERA 5 around Europe. So here's the first example of what a lot of the plots will look like. So here we have the Weibull distribution fits. Now, you've got, this is for Pontevedra on the left, and there's 12 months, and Vigo is on the right. Now the black line is the observational data. So this is the observational fit of the distribution to the distribution. And in orange is the ERA interim fit for the grid box where that station is on a half by half degree latitude longitude basis. Now the green is what we're doing then to ERA interim, and we call it adjusted ERA interim, where it's moving the distribution towards the observations. And you can see for Pontevedra and the 12 months is doing a fairly good job. It doesn't always get the peak of the distribution, but it's clearly moving the orange line towards the green line. Now the red line in these plots means that this is the WFDEI data set. So it's clearly not the same as ERA interim, unadjusted, but it's similar, and it's the distributions are similar. WFDEI is slightly more peaked, slightly more like the observations than the unadjusted ERA interim, but still not as close as our green distribution is to the black observations. So that's Pontevedra, and this is a station that seems to be working quite well. And a lot of the stations look like this around Europe. But we've noticed that there's a few stations, and one of the good examples of this is Vigo, where you can see here that the adjusted green data is over adjusting. It's pulling the ERA interim data further to the left of the observations, and WFDEI is being pulled more to the left as well. Now this may be due to a number of factors, and one of them could be that the station data are sort of much less representative of that location, or else another thought is the distributional fits are not doing that well here in terms of truly fitting the observations. So you've got one good station and one poor station here in terms of fits. If we look at other parts of Spain here, and you can see that was a much windier part of Spain in the northwest. This is a less windy part in Santander in the north near the French border. And here you can see again the observations in black. The green line, the adjusted ERA, is moving towards them, but not always perfectly, but moving towards them. And here WFDEI is a much closer to the unadjusted ERA interim. And here's another station in southern Spain at Gibraltar. And here you can see the observational distribution is quite different. It's more like Santander than the ones in northwestern Spain. But still the adjusted ERA interim is moving the reanalysis data closer to the observations. But it's not getting this sort of flat or almost bimodal distribution. It's not doing that. And also the WFDEI data is changing ERA interim quite a bit as well compared to what it was doing in Santander. So that's one way of looking at the comparisons of station data with the reanalysis. And here's some more in Portugal. So on the right is Porto, and the point further north of Porto is Viana do Castelo. And here you can see that the adjusted ERA interim has moved closer to the observations at this site in northern Portugal, but it's slightly overdone it again at Porto. It's moving it more to the left. So this means it's further reducing the ERA interim wind speeds. And also in a similar way to the stations in Galicia as well, the WFDEI is becoming more peaked in terms of the distribution compared to the original ERA interim for the half-degree grid box where Porto and this other site are located. Another way of looking at this data is to directly compare the data as a scatter plot. So this is taking all 6 hours, all 6 hourly values during here in March for the whole period of record from 1979 to 2016. So there's an awful lot of dots here, and on these plots, this is the unadjusted ERA interim on the left-hand side for Vigo compared to the WFDEI. Now the green line is the one-to-one line. So, and the red line is the regression fit between these dots. And you can see that here is a good example of a station that's quite different from the ERA interim wind field. It's much weaker winds because the lines are well below the green one-to-one line. But you're comparing unadjusted ERA interim here with WFDEI, which is based on unadjusted ERA interim. On the right, also for Vigo, we have the unadjusted ERA interim data again against the station data. And you can see here that this is not, in some parts of the year, there's very little correlation between ERA interim and the observations at Vigo. So the regression fit is firstly a straight line. It's not much, there's hardly any correlation. And the one-to-one line, you can see there's a lot more dots below the one-to-one line than above in most months. So that the station has a lot smaller wind speeds than ERA interim. Now looking at how the unadjusted and the adjusted ERA interim look for some other sites in Spain. So this is Pontevedra in the northwest of Spain and Vigo again. So on the y-axis we have unadjusted ERA interim, and on the x-axis, or on the y-axis we have unadjusted ERA interim, and on the y-axis we have adjusted ERA interim. So you can see here that the one-to-one line, the adjustments for Pontevedra are making the wind speeds a lot less than they have been produced by the reanalysis. So the adjustments are reducing the wind speeds. And this is more so in the windier winter months and less in the summer months when the wind speeds are lower. Vigo is doing the same thing. Bigger changes, bigger adjustments in the winter and smaller adjustments in the summer. And if we look at these plots in Portugal as well, they're doing similar things, although the adjustments are not quite so much. There are less adjustments at Porto because they're not so far beneath the one-to-one line, but the adjustments are larger, like Pontevedra at Viana do Castelo. So I think there's a number of issues with the sites here and exactly where they are. Some may be coastal, some may be more inland, and so we need to look at that a bit more. But we're just looking at one small part of Europe here. We need to apply this to many more stations as well. Now, coming to the final part of the talk, we're going to look now at the direct comparison now of ERA interim with ERA 5. And this is over this 7-year period from 2010 to 2016. So on the left, you have January. So this is the average of the January data from every 6 hours, because that's what ERA interim is, for that 7 years. So this is 7 Januaries, and on the right, you've got 7 Julys. Now, if you look closely at the colors, the greens and the blues are where are negative numbers. So this is where ERA 5 is less windy than ERA interim. And over much of Europe, with the land areas, that is the case. Even in July, although the differences are smaller than in the winter months. And the blues are these larger differences, and the differences are much larger around coastal areas, particularly in northwestern Britain, northwest of Europe, in Britain and Ireland, in Norway, Iceland, and around some of the West European coasts in France and Spain, and also in the Mediterranean. What you also notice here, which is common to all months, is that ERA 5 appears to be windier than ERA interim on the offshore, so around the coastal parts of the Mediterranean and off the coast of Norway. So when you're comparing a gridded data set with another gridded data set, we're only just changing the resolution slightly. You can do this comparison over the marine areas too. We're not all our other work has been restricted to where the land stations were. So we waived that restriction. So we are looking at the whole domain here and not just at where stations are. So this is why we're showing things over the Mediterranean, showing things over the northwestern Atlantic or northeastern Atlantic. So these tells us that era 5 is less windy than era interim over this 7-year period. And this would also be a good thing to repeat when the full period from 1979 is available from era 5. But we can also look at scatter plots. And we're looking at scatter plots again here. These are direct comparisons now of what the grid box where Vigo is. So it's nothing to do with Vigo. It's just happens to be where that point is. It's era 5 against era interim, and era 5's on the x-axis and era interim's on the y-axis. And you can see here the green line is still the one-to-one line and the red line is the regression fit. And you can see that most of the era interim grid box data is above the era 5 data at Vigo. And so this means that era 5 is less windy than era interim at Vigo. If we move to a site in southeastern Spain at Murcia, the differences are smaller. It's obviously a lot less windy here, and but for most of the months of the year, there's little difference between the regression fit and the one-to-one line. So era 5 and era interim are closer to one another in Murcia, but era 5 is a lot less windy in the northwest of Spain. And we're going to look at a few other sites now, places that are much, much windier. So this is looking in the northwest of Scotland at Stornoway on the island of Lewis. Here again, a lot of the era 5 data is above the line. So this means that it's less windy than era interim at Stornoway. And Stornoway is on the island of Lewis. It's probably a land box within both reanalyses. Whereas if we've got another station here in the northwest of Scotland called Tiree, which is on an island further off the mainland. And though this may be an island, a marine box without any land, but here there's very good agreement between the two reanalyses. The regression fit is very close to the one-to-one line. And then finally, looking at some other sites. This is a site in southern Sweden at Linköping. And again, there is some tendency for era 5 to be slightly less windy. But it's not such a windy site as those ones in Scotland or in Galicia. And on the right, you've got Grosseto, which is roughly between Rome and Pisa in Italy. And again, the distributions and the regression fit and the one-to-one line are relatively close. So era 5 is relatively close to era interim in this part of Italy. So there are hundreds and hundreds or thousands and thousands of these plots we can produce. So our ESEM bias adjustments were updated to 2017 when the paper came out. So they're available from 1979 to 2016. We could adapt this approach, and we probably should do when era 5 is fully available. And the bias adjusted data is available, the top bit is available at this website, and it should eventually be available through the Climate Data Store of the C3S projects. And also all the country and cluster averages that were produced for the demonstrator are also available here as well. So but the key point in the second part of the talk is that based on this 7-year period, era 5 is a lot less windy than era interim. And it's particularly so for the more windier parts of Europe and in the winter months as well when wind speeds are higher. So more for extreme winds than sort of less extreme winds. And there's a lot of issues about the uncertainties for some of the sites where they can be large locally. They might be less representative. And we still noticed, even in doing some of this work, that the quality of the observational data series can be a problem. If you go back and look, you'll notice that there's a few points in Vigo where there appears to be outliers in the observations. We spent an awful lot of time early on in the project trying to get rid of outliers and bad data from the HAD-IST data set. And we achieved most of that, but there's still some observations which are clearly wrong in that data set that need to be screened out. So thank you very much, and I'll hand you back to Alberto.
Okay, excellent presentation, Phil. And this is again just a glimpse on the huge amount of work that's been done on this climate variables during ESEM. And now we have about 10 minutes for questions. If you would like to submit your questions through the question tab on your GoToWebinar control panel, we'll take the questions, and I'll try to copy them over to the presentation that you can see as well as hearing about it. So I'm just waiting a minute so that people can type their questions. We're receiving some, so we'll just take 1 minute to write them. Okay, so maybe do you like Phil to address this question, or I can add a bit? Yes. Okay. So we looked particularly. This is work that is done under the work package 3 and it's under the energy variables. There hasn't been an extensive testing, so that still needs to be carried out in a more systematic way. But what we've observed is that once we get to the conversion into energy variables, it's not always clear that there is a benefit to the conversion. And it's partly to do with the assumptions we make also on the conversion, and partly to do with the resolution we are using, because we're not resolving individual wind farms. And so I would say that we have a partial view at this stage. Certainly, I would say, given the large adjustment that Phil has just shown, we certainly expect that we will see some changes, large changes to wind, because of just the conversion to the cube of the wind. And but it's not entirely clear that that will produce better winds overall, better wind power estimates overall. So we can, I think we can share some of the analysis, and some of the results are also available in the webinar that was given on energy variables. Again, you can look at our website, and there's a recording as well as the presentation. So that's a presentation given by Dr. Laurent Dubout, and he presented extensive results on the conversion, as well as some of the comparison with between adjusted and unadjusted. So we have another more general question. Would you like to take this one, Phil?
So this question is, would the time series at higher spatial resolution be available as opposed to the country and cluster average areas, which is a much more coarser resolution? The data are available because we have, I think we have put the full data set there, so it is possible to get the data out. But I have to admit, we haven't made that very easy, because you have to deal with very large data sets. But it is possible to get those numbers. So I need to probably talk to Alberto about that to make sure that they are available on the last link that I had up at the end of the talk. We certainly got the data. It's just a matter of making it available. We haven't looked separately at these different the 4 6-hour observations at 0, 0, 0, 6, 12, and 18. I mean, we haven't looked at all at the diurnal cycle in ERA 5 to see whether it's good or as good as ERA interims appeared. So this is another bit of work we need to do, but that could be a factor. We do know from looking at some of the station data across the British Isles in another project that there are surprisingly large diurnal cycles of wind speed, which surprised me when I looked at some of the data. So it's just something we need to look at, because if ERA 5 has not got the diurnal cycle right, then there could be issues with that. And obviously, I think this is something that ECMWF will be looking at in their analysis of ERA 5 when more of the years are available. So that is a very good question, number 3.
Okay, thank you very much, Phil, for the answers. And I'm going to move on now and just give you some final comments before we close. And I just want to specifically mention a couple of activities. So in terms of the ECEM itself has now concluded formally, but we are keen to communicate what we've been doing during ECEM, and that's also one of the reasons why we have organized this webinar. We'll probably won't do any other webinar under ECEM, most likely. In fact, probably it's not going to happen under the ECEM banner, because also the ECEM phase, which is a pre-operational phase, has completed now, and C3S is now moving on to the operational part. So we would like to consider this is going to be the concluding webinar for ECEM. And we want to, first of all, point also to other relevant events you might want to attend that provide additional information about this link between climate and energy. There's a training course in Shanghai between May 18 and May 20, organized between WMO, WEMC, GFCS, BSCC, and with contribution of C3S as well. And soon after that, 2 days later, we have the International Conference Energy Meteorology also in Shanghai at the same venue. So, so there's still time to register and to come along, also time to apply for your visa and so on. So if you are interested, please get in touch or register directly on the website. I would say in terms of webinars, I encourage you to look and monitor the C3S website. So this is the climatecopernicus.eu. They will provide updates on activities that are happening under energy sector as well as others. But we will continue to support the activities under C3S Energy, and we want to make sure that what we developed in ECEM will continue for some time to come. And the webpage is still available, will be there also, as well as the demonstrator, which you can access through the web link here. And other general information on the project is available at the webpage below. And if you have any other questions, please get in touch with us. The contacts are also on the web. And I'd just like to acknowledge the contribution to this webinar by the World Energy Meteorology Council, with the link here. So this concludes our webinar. I would like to thank again the two excellent speakers, as well as all of our attendees and the questions that have been asked, and the interest that you demonstrated by following us over also the previous webinars. I've seen people that have attended previous webinars as well. So thank you very much again for your attention, and watch the space through particularly the C3S website and ESIM for a while as well. Okay, thank you.